within 1 year. If you accelerate at 1 g, which is very comfortable,
you reach the speed of light.
You reach the speed of light.
Right, and in 20 years, you will reach the edge of the universe.
Exactly.
Right.
Exactly.
Welcome to Harvard University. I'm here to interview Professor Avi Loeb, the longest serving chair of Harvard's astronomy department and world-renowned eminent astrophysicist. I first emailed him in 2020 when I was a student at Brooklyn Technical High School. I shared my idea of using a black hole as a gravitational slingshot to travel to the stars. And to my amazement, Professor Avi Loeb responded. He said, "Dear Rafaf, thank you for sharing your interesting idea with me. As it turns out, this idea has already been explored in the scientific literature. I attach one of the papers that discuss it. As it turns out, that paper was a 2015 paper that Professor Loeb wrote with his postdoc, James Guilichon." Professor Avi Loeb's latest book, Interstellar, will be released on August 29. Greetings from Harvard University. This is Rifat Bari from the City College of New York. Today I'm very honored to have our guest, Professor Avi Loeb. Professor Loeb is the longest serving chair of Harvard's astronomy department. He's the Frank B. Baird Professor of Astronomy at Harvard. Of course, he's also the founding director of the Black Hole Initiative and the director of the Galileo project at Harvard. So I'm going to have the chance to ask him many questions on Oumuamua, aliens, and beyond in today's episode. So Professor Loeb, thank you for joining me.
Thanks for having me.
Thank you.
You could have introduced me in a shorter time by saying that I'm a curious farm boy. I was born on a farm and I was always curious about nature. And that guides me throughout my life. I don't have any social media. I don't care what people, how many likes I have on Twitter. I just want to figure out the reality that we live in.
You know, you wear many hats. You're the director of the Black Hole Initiative, the Galileo project. But thank you for taking the time to correspond with me for the last 3 years.
Oh, it was a pleasure.
I first emailed you when I was a high school student at Brooklyn Tech. My idea was to use a black hole as a gravitational slingshot.
It's an excellent thing.
And you responded, you said, actually, Rifat, this idea has been explored in the literature. Yeah. I attach a paper that discusses it. And it was a 2015 paper with you and
James Guilichon.
Right, that's how you pronounce it.
Actually, he was my postdoc, and at the time we also wrote the paper on the light sail. So when I mentioned that with one of my postdocs, I wrote the idea of a light sail, it was with James Guilichon around the same time.
Professor Loeb, I'd like to talk a little bit about your work on black holes. You know, you're the founding director of the Black Hole Initiative at Harvard. And in fact, Stephen Hawking came to your home to celebrate that initiative. So I'm honored to be in a place that was near where Stephen was.
In fact, he came through this porch, through the door, because we had to build for him a path that he could go on with his wheelchair.
Good evening, and thank you to Avi and Alfred for hosting this evening's Passover celebrations. Thanks to Avi, Andy, and Yuri Milner, I am here again and hope to return soon in support of the new Black Hole Institute.
We will be delighted to host you every year, and assuming that you will not solve the information paradox very quickly this year, there will be a lot of opportunities for you to work with Andy and Malcolm in future years, and we will be delighted to have you every year.
That's very nice to hear. Sounds a little bit like Sir Isaac Newton. He was a little boy playing with pebbles on the seashore.
Yeah, except I play with pebbles that come from interstellar space, that from outside the solar system, and I'm not trying to imitate anyone from the past. I'm just maintaining my childhood curiosity, because when I was a child, the most frustrating thing I faced was coming to the dinner table and asking a difficult question, and the adults in the room would dismiss the question because they didn't know the answer, or they would invent some answers. And it was clear to me that they're faking it, and I was upset about it and frustrated, and I decided to look for the answers myself by becoming a scientist. And guess what I'm finding? I'm finding a lot of my colleagues behaving like the adults in the room, inventing answers that they don't really know without relying on evidence, which is the scientific method.
So you've come full circle.
Well, I'm still working on my colleagues, trying to educate them, and we can talk about it more. I went to the Pacific Ocean on an expedition a couple of months ago, and It was a risky expedition because we were looking after tiny droplets that melted off the first interstellar meteor, the first object from outside the solar system that collided with Earth about a decade ago. And it was difficult to find them because it was a region 7 miles in size, and the ocean depth is more than a mile. And looking for tiny droplets the size of a grain of sand was very challenging. But I took the risk. We found them. We found more than 700 by now.
Spherals.
Spherals, yeah. And 650 were found by a summer intern that worked with me, Sophie Bergstrom. And we analyzed those spherals. We can talk more about what we are trying to find. But it's a teaching moment of showing to the public how science is done, by taking risks, by looking for the answers from nature, not assuming in advance anything. And moreover, trying to learn something new, which to me is all the fun, because pretending that we are experts, that we know the answer in advance, that we are very proud of ourselves is really not the right approach, because we know very little. We don't know what most of the universe is made of. Actually, it's dark matter, a substance that we've never witnessed in the solar system. So let's be modest and let nature educate us. And that's the spirit of this expedition. I am a theorist, a theoretical astrophysicist, and I went there, did an experiment with a group of 28 people. I led them. I was the chief scientist on this ship that was called the Silver Star that we had for 2 weeks. And and now we are getting the results. They will be posted out very soon, by the end of August 2023. And it's very exciting to be engaged. It's just like a detective story. So I'm showing to the public. I wrote 43 diary reports in medium.com, and I got lots of fan mail. The diary was read by millions of people around the world. It was translated to Spanish. And it's a way of illustrating to the public how science is done, by sometimes making mistakes, taking risks, eventually finding the answer from the evidence, like a detective story. But I'm also using it to educate my colleagues in academia, because they often pretend to be the adults in the room. In fact, on the day that I came back from the expedition, there was a paper published in the Astrophysical Journal saying that this particular meteor is actually not from outside the solar system. The US satellites, the US government made a mistake, they say. The speed of this object must be 3 times smaller, and then it would be just a stone that belongs to the solar system, things that we've seen before. That's the only way they can fit the data with a model for stones, familiar stones. And so I knew that it's not a stone, because we collected those spherals, and on the ship itself, we already knew that they're made mostly of iron. And these people said, no, it cannot be made of iron. So it's really a little bit, how should I say, sad to see colleagues, scientists who pretend to be experts, write a paper, and the paper is reviewed by other colleagues and accepted for publication. And it's published on the day that I'm coming back with the material in my hands, knowing that it's wrong. But yet they prefer to subscribe to past knowledge instead of saying, this is great, let us see what he finds. And also people before I went there said, it's a waste of time, waste of money, why would you do that? And I said, you just relax, sit back and wait. I'm not asking you to do anything. I'm doing the heavy lifting, going there. And if I come with nothing, you can say that's what you expected. So, it really frustrates me that some people are negative when it's actually the scientific process to be optimistic, to be positive, because life is a self-fulfilling prophecy very often, that you have to be positive in order to find. You have to search in order to find something. If you don't search, you will never find anything.
Just like the church during Galileo's time.
Well, that's again another historic analogy. And there, the connection is that there, humans preferred to think, people around that time preferred to think that we are the center of the universe. Now, religion argued that for a good reason. They wanted people to believe that God looks over their shoulder, that they're really important. because that's the way we are brought up as kids. We have parents looking over our shoulders. When we become adults, suddenly you have to take care of yourself, and as an adult you're looking for someone stronger than you that is looking over your shoulder. So God is a good solution, and that's what religions are tapping into psychologically. And so people subscribe to that idea and say that's great, but for that to be the case, the Earth needs to play a special role, because imagine the billions of planets in the Milky Way galaxy. If God has to pay attention to all of them, then the Earth cannot be at the center, like that. But anyway, that's what people believe. They said Earth is at the center, and then of course Galileo argued otherwise, and today he would have been canceled on social media. And back then they put him in house arrest. Basically, nobody would listen to you. We don't allow you to communicate your views. That's what they said to him. And they refused to look through the telescope for the reasons that he was basically seeing the moons of Jupiter orbiting Jupiter. And he said, well, if they're orbiting Jupiter, then the Earth cannot be at the center. Why would other bodies orbit Jupiter if Earth is at the center? Everything should orbit Earth. And suppose that we would maintain the view that Earth is at the center today, and we would send rockets to Mars, we would never reach that destination, because we would think that Mars moves around the Earth. We would shoot the rockets and it wouldn't reach anywhere. So my point is that it's really important to adapt to the reality, even if it's not flattering. When you look at the mirror, it's better not to put makeup, but to realize who you are. And it applies to everything in life, because then once you understand it, you can do things that will allow you to accommodate the reality. And that's the importance of science, that it allows you better understanding of reality. So we are not at the center of the universe, we are orbiting the sun. Once you understand that, you give up on your importance, but you benefit that now you know how to launch a rocket to Mars. I mean, that's that's a thrill. And also, if we realize that we are not the only ones, that we are not alone, that we have a neighbor in a cosmic sense, we could go there and visit that neighbor. We could learn new things from the neighbor. If the neighbor is more advanced than we are technologically, we might have a glimpse at our technological future. It could be used to make money, because if you get some technological gadget from some civilization that preceded us by 1 billion years, and they are much more advanced than we are, then you look at that and try to reverse engineer it, basically try to learn how that was made, and then you can make money out of that.
Right. And in fact, when you were talking about Galileo, not only was he under house arrest, but he died under house arrest and blinded at the end.
Yeah.
But even at the very end, he said, yet it moves.
Yeah,
right? And
exactly.
Just like you say with Oumuamua, yet it bends.
Yeah, so only over the one thing to recognize, only over the past decade, we had the instruments that allow us to discover objects from outside the solar system. So, when Enrico Fermi, 70 years ago, he said, where is everybody? He had a discussion over lunch with colleagues about extraterrestrials. And he said, well, if they're out there, where is everybody? And, that's just like a person staying at home, single, and saying, I don't have a partner because nobody is next to me. Well, to find a partner, you need to go to dating sites. You need to look through your window. You need to maybe go out to your backyard. I mean, you can't just say, where is everybody? That makes no sense. Yet, nevertheless, for 70 years, people ask, where is everybody? As if, a spacecraft will come from thousands of light years away just to visit Enrico Fermi at lunchtime in Los Alamos. Why would he do that at that time? The time is measured in billions of years in the universe, and the distances.
To think that they would come that far and at that particular time.
Exactly. And also you have to engage because of the huge dimensions of space. You have to seek evidence. And what I'm saying is only over the past decade, we were able to discover objects that arrived to the solar system or near Earth from outside, only over the past decade. So one such telescope was in Hawaii called Pan-STARRS, and it discovered Oumuamua by chance because it was looking for objects that pass close to Earth. They're called near-Earth objects for a good reason. We know that the dinosaurs were killed by a giant rock that's the size of Manhattan Island that collided with Earth 66 million years ago. the dinosaurs were not very smart. They didn't look up. They didn't have astronomy. Didn't have telescopes. So they missed an opportunity to stay around and they died. We have telescopes. We are smarter. We can figure out if something is approaching us and maybe do something about it. So the point is, this telescope was constructed to find the near-Earth objects that are bigger than the size of a football field. And there came this object, the size of a football field, Oumuamua, that reflected sunlight and was passing near Earth within a sixth of the Earth-Sun separation. It was moving too fast, actually, to be bound to the sun. It actually was able to escape.
So even after you accounted for gravitational acceleration, it was moving too fast.
Oh, no, it was moving too fast just from gravity, relative to gravity, not speaking about that. On top of that, there was something unusual about it. But what I'm saying is, originally, they just measured the speed of it without measuring the acceleration, just the speed. And the speed was enough for this object to escape from the gravitational pull of the sun. So that indicated that it's not bound to the solar system, it came from outside, okay? Just like a rocket, if you launch it fast enough, it escapes the gravitational pull of the Earth. So the same is true for the sun. And that was the first report about an interstellar object. And I was intrigued because I wrote a paper a decade earlier predicting that this telescope, Pan-STARRS in Hawaii, will not find anything because we used what we know about rocks in the solar system, and we said, suppose other stars are like the sun and they have rocks around them, the same number, what would be the chance of Pan-STARRS seeing one of them flying through? And we calculated that it's less than 1% chance. And then they find Oumuamua, so that was intriguing to me because my prediction turned out to be wrong, so you learn something new. Maybe there is a new source of. But then as more data came about this object, it looked more and more peculiar, unlike asteroids, because, for example, it had a shape that is very extreme. When it was tumbling every 8 hours, the amount of sunlight reflected changed by a factor of 10. And the analysis of the reflection of sunlight implied that it has a disc-like shape, flat shape, like a pancake, as it was tumbling. That's strange because most of the rocks that we see, asteroids, change the amount of light reflected from them by maybe up to a factor of 3, not factor of 10, as Oumuamua was. And then there was a push of Oumuamua away from the sun by some mysterious force.
But there was no cometary tail.
No evaporation, yes. So you could think, oh, maybe it evaporates and then it's just like a rocket, that the gas that evaporates backwards is pushing the object forward.
Was that the idea behind the hydrogen iceberg, that it evaporates and...
Yeah, so some people... So first of all, when that was recognized, immediately I was intrigued, and I thought, what can push it if there is no cometary evaporation? And my only possible explanation was that it may be pushed by reflecting sunlight. And for that, the object had to be very thin, like a film or a membrane or a sail pushed by light. And that's called the light sail. Or it could be just the skin of a bigger object that was torn apart, like a broken piece of a bigger object. At any event, it has to be thin. And I said, nature doesn't make such things, so maybe it's artificial, maybe it's technological. And then 3 years later, the same telescope in Hawaii discovered an object that was pushed by reflecting sunlight, but had no cometary evaporation at all.
Was that the Borisov?
No, it was called 2020 SO, and it was discovered in September 2020.
That was one of NASA's rocket boosters.
Yes, exactly. It was launched in 1966, and we know that it was made of stainless steel. That's why it didn't evaporate. But it also had thin walls, and that's why it was pushed by reflecting sunlight. So exactly the concept that I suggested for Oumuamua. So we know that this one, 2020 SO, was technological in origin because we produced it. The question is, who manufactured Oumuamua? And there were some other anomalies about Oumuamua that I mentioned in my book. But altogether, it looked weird because it didn't appear like a comet, didn't appear like an asteroid that we're familiar with. And then my colleagues insisted that it must be natural, so they had to come up with explanations to these anomalies. And one of them was, as you said, that it's maybe a hydrogen iceberg. So it's a comet, but of a type that we've never seen before, made of pure hydrogen. It cannot be made in a planetary system like the solar system. It has to be made in a molecular cloud made of hydrogen. And we've never seen anything like that. And the idea was that when the hydrogen evaporates close to the sun, it gives it a push, just like a comet, but hydrogen is transparent, so you can't see it.
Oh, I see. Okay.
So the problem with this model is that such an iceberg made of hydrogen would not survive the journey because hydrogen evaporates very quickly. We showed it later in a paper, and the authors of that model agreed that it cannot survive. So then another group said, well, maybe it's a dust bunny, a collection of dust particles, very loosely bound, that like you find at home, except it's the size of a football field.
Held together only by gravity.
No, it's not gravity, it's just very loosely bound with connections between the dust particles, like a dust bunny you find at home.
Okay.
And then it just floats through space like a cloud, and then because it's so lightweight, the reflection of sunlight is pushing it. That was the idea. The problem is when it gets close to the sun, it will be heated by hundreds of degrees. And because of that, it's unlikely that something that is 100 times less dense than air, which is what you need to get enough push, 100 times less dense than air would survive and not disintegrate. That's very unlikely. So then another group said, oh, actually, maybe it's a nitrogen iceberg. We found it. Because we know the surface of Pluto is made of solid nitrogen, and maybe you chip off the surfaces of planets like that, and then you end up with interstellar objects made of nitrogen, and they evaporate. Again, it's transparent. So we did a calculation of how much nitrogen you should expect in the entire Milky Way galaxy if you chip off all the Plutos that might exist around other stars, and it's not enough. You cannot account for a big enough population that would explain Oumuamua as one of the such objects. So then, most recently, a few months ago, there was a paper in Nature, very prestigious journal, saying, oh, we figured it out. And that's already 5 years after the Oumuamua was discovered. The community kept insisting it must be natural, it's obviously natural. But if it's obviously natural, why do you need papers after papers for 5 years? If it's obvious, you know? Anyway, so the last one, and everyone cheered up, yeah, now we know it. It's actually a water iceberg, just the type that we see. Okay. And the idea was it's going through interstellar space, and cosmic rays, energetic particles, bombard it, and they break the water molecule into oxygen and hydrogen. Okay. And then the hydrogen goes to the surface, and when the object comes close to the sun, the hydrogen evaporates, and just like the hydrogen iceberg, you get propulsion without seeing the cometary tail.
Okay, but what is the role of the oxygen? Why do you
just because you want to start with water. Okay. So they say water icebergs are common, there is no problem making them, we see them in the solar system.
Okay. So it combines the best of both hypotheses.
Yeah, it says it's
seen it before.
Yeah.
And it's transparent.
Yes.
Okay.
The only problem is, a day after this paper was published in Nature, right, when some reporters showed it to me, or I saw it actually, it appeared, within a day, we realized that they made a mistake in the energy equation of the energy balance. Because what they did was equate the energy coming in and hitting the object from the sun to the energy radiated away from the surface of that object.
Okay, well then it would be an equilibrium. It wouldn't heat up, right?
No. It would, if when it comes close to the sun, it will get warmer. That's okay.
Okay.
But they forgot to include the energy that you need to invest in releasing the hydrogen out of the surface. Okay. So it's just like you get a salary and you say, okay, I can support myself. I can pay for the utility bills. I can pay for the fuel of my car. But then you forget that you have to eat. So suddenly you don't have money. So it's the same thing. They accounted for two things, energy coming in from the sun and energy radiated by the surface, to calculate the temperature of the surface, and they said it works. But then we said, oh, but if you take the energy that you need to invest in releasing the hydrogen atom, then this term is actually millions of times bigger than the ones you included at the temperature that you calculated. Therefore, it makes no sense. So when you include that term, it turns out the temperature is much, much lower by almost a factor of 10. And that means that there is very little evaporation from the surface. You cannot get the propulsion that you need. So within a day, we posted that paper. We submitted it for publication. And I wrote emails to the journalists, the science journalists that reported the day before in all major magazines, including Scientific American, the New York Times, Wall Street Journal. All of these said, problem solved at last. Oumuamua is a water iceberg. Yeah, we found it. And they cheered. They didn't ask me for any comments, these journalists. So I write to them a day later and say, look, this paper that you celebrated made a mistake. So one of them says, oh, thanks for letting us know, but we don't want to confuse our readers. We will not comment on that. And I said, you don't need to agree with me. You can just put a footnote that says, Avi Loeb wrote a paper which points out this and that. You don't take responsibility. You just say that. No, they don't want to confuse the readers. The readers will be confused. So
then they're not giving enough credit to the public to understand how nature behaves.
That's exactly the point. You want the public to hear just one narrative, even though it might be false.
I mean, it's not about being confused. It's about hearing the truth.
Exactly.
The truth doesn't bend to what the public or whoever wants it to bend.
Down at and saying, we want the public to believe a narrative that we want to deliver. And these are science journalists. Now, if we complain about politicians not adhering to evidence, there was a lot of discussion during the pandemic, during global warming, we say politicians are not paying attention to scientific evidence. These are science journalists that are not paying attention to scientific arguments, okay? Science journalists saying to me, we don't want to get our readers confused. Now, there was another science journalist that said, I contacted the authors of that paper and they said, no comment until their paper is refereed. We don't want to say anything because maybe there are some issues with it, which is a political answer. Like, suppose someone says 2 + 2 is 5 and you know that it's 4. You are not saying, I wait until this paper is refereed before I would address that. You just say that is wrong because if I take 2 apples and 2 apples, look, I take a photograph with my cell phone and it's 4, it's not 5. You can show that. So why argue about, okay, no, they said until it's refereed, okay? Which is a strange thing for, okay? So the science journalist said, that's what they said to me. I want to wait. I said, okay, let's wait. 3 months later, our paper got accepted for publication without much changes. Okay. I write back to this journalist and say, here you have it. It was accepted for publication. No reply.
Oh, no.
So that's the bottom line. The original reports came about this solving the mystery, and our paper is published showing that there is a mistake in this paper, and since then, never heard back from those authors. Okay, so just to illustrate to you, the truth is not always apparent, and it's not always a fair game of exchange of ideas. Sometimes it's a narrative that some people want to convey, and they are cheering up and down, saying, yeah, we solved it, and when you show them that they didn't solve it, they don't say anything, which is not the sincere way. When I went to the expedition, I was looking for these spherules, and on the 6th day, we didn't find them. So I wrote an essay on medium.com, a diary report on the 6th day saying, where are the spherules? I was sincere about it. I was telling the public we didn't find what we were looking for. A day later, we found the spherules, and we can talk about it. But the point is, the way I see it, and maybe I'm naive, but what you see is what you get when you speak with me. Now, I may be wrong sometimes, that's okay, but I'm telling you what I think. And, that's the approach of a kid, by the way. It's not trying to manipulate people. I'm telling you what I think. But there was a New York Times article just last month about the expedition. Yes. And it quoted some of my colleagues. And one of them said,
I am sick
Yes.
of hearing Avi Loeb's
now,
claims. Yeah.
I wish him prosperity, success, happiness. Why is he sick by me discussing a possibility about an object, and not only discussing the possibility, but actually putting time and effort to look for the evidence? Why is that sickening a scientist? A scientist should be thrilled. You know, it reminds me in the case of Oumuamua, when we had a lecture at Harvard University about all the anomalies of Oumuamua by a scientist. And when I left the auditorium after the lecture, I went together with a colleague of mine that worked on rocks for decades. And he said, Oumuamua is so weird, I wish it never existed. So that shows you the frame of thinking. And a psychologist explained it to me, distinguished psychologist Mahzarin Banaji, a colleague of mine at Harvard. She said, this is called cognitive dissonance, when you're faced with two things that create a conflict for you. So in the case of Oumuamua, it's the evidence, and then your insistence that you already know the answer, that it must be a rock, because you worked throughout your life on rocks. You are not involved in this, so everything must be rocks. You know, like, why would anything be different than rocks? And I call that the Stone Age of science, when people insist everything in the sky is stones. And unfortunately, you know, you would think that we learned from history, from what happened with Galileo, to be open-minded. After all, academia is all about blue sky research, you know, being open-minded, you know, and tenure is given to professors so they can practice what they believe is true without worrying about job security. Okay, that's the whole idea of academia. Why do we have academia? So people can pursue the truth, right? Not worry about what other people say. But instead, what I face is when I'm trying to pursue the truth, other people are getting sick.
You know, this is so. I never thought of academia as this way, but you know, it seems when you're at the cutting edge, it's not just physics or science,
No, it's
but
jealousy. It's jealousy.
but another layer of politics.
Well, I'll explain why. Because the public cares a lot about this subject.
Right, right.
The public, young people, now the government, we can talk about it. In Washington, D.C., there were hearings at the House of Representatives,
Right.
and the word extraterrestrial technologies,
Mm-hmm.
you know, was mentioned in the discussion. So if the government talks about it and the public talks about it, it sounds to me like common sense that scientists should get engaged and help. Because the government is not a scientific organization. So
Right, right,
this is something worth contemplating, worth discussing.
right.
The possibility, I'm not saying we have definite evidence, but the possibility that there might be objects in our backyard, this is my backyard, that may represent a tennis ball that was thrown by a neighbor. Why
Right.
not? Like, why is that so, why is that a wide speculation?
Taboo.
We sent out 5 probes to interstellar space.
Right.
You know, we can imagine our neighbor doing the same, and one of the tennis balls from a neighbor arrives to our backyard. Like,
Right,
why
right.
is this? You know, people are, in physics, people are talking about speculative ideas like extra dimensions, string theory, the multiverse. These are ideas that were not tested experimentally at all. We don't have any proof that extra dimensions exist, extra spatial dimensions.
Right.
Nevertheless, it's part of the mainstream discussion for several decades now.
Yeah.
Okay, 4 decades. And moreover, I should say, there is no hope that during the lifetime of the practitioners, we will have an experiment that will test their idea, show whether it's right or wrong.
Right.
And moreover, I should add, they are happy about it. A happy theorist is a theorist that will never be proven wrong. So without having the guillotine that will chop off the head of an idea so that you will realize you have to work on something else, great, you can work on this, do intellectual gymnastics and show off that you are smart. You know, that if your objective is to show off that you are smart, you will do 2 things. One, work on very advanced mathematics and talk about extra dimensions that cannot be tested. And then you show that you are smart, you will never be proven wrong. It's a perfect situation. You feel like part of the elite. And moreover, you feel smarter than the public. And when you feel smarter than the public, you are also not paying attention to what the public cares about. So here I am caring about what the public says. exploring it scientifically by collecting evidence, not by doing string theory where nothing will be tested. I'm actually going to the Pacific Ocean for 2 weeks, raising the $1.5 million necessary for that, and collecting a group of the best professionals in the world, 28 of them, to come with me on a boat. We find those spherules, we are testing, and that makes Steve Dash sick. Now I ask you, how is that possible? The answer is because the public cares about it. It resonates with the public. I get attention. The fact that I get attention makes him and others upset. It's not about the science. If I was in the shadows, in fact, one of my colleagues was quoted in the Crimson, the Harvard Crimson, as saying, it's about time that reporters will pay more attention to boring science. He was saying, it's true that there is some jealousy in the way we respond to what Avi Loeb is doing. Right. It's true. But it's about time that science journalists will pay attention to boring science. And I say, why should they pay attention to boring science if it's boring? You know, why don't you work on exciting science instead of asking the reporters to pay attention to boring science? And this is a question of, are we alone? Is a question that resonates with the public, a question that we can address given that we can find those interstellar objects. And in the expedition, we show that we can use microscopes to answer this question, not telescopes. It's a completely different window of doing that. So, you know, why is that a negative that I resonate with the public's interest? I connect to it. I invest a lot of time and effort in actually doing the science. I'm not a blogger that is, you know, there are some bloggers that didn't write a scientific paper for more than 10 years. Right. One of them heard me say that, and he used his Twitter handle to be a blogger that never published in the past decade. And as if ignorance is something you should be proud of. Like, you know, you look at soccer player that play soccer. And, you know, the audience looking at the soccer players can say, oh, that's not the way to play soccer. You should have passed the ball this way and that way. And I say, who are you to tell me how to play soccer? Like, if I'm in the field, so I'm a real scientist. I publish papers all the time. You can check on my papers. And this is a blogger who is just a commentator from the audience. Right. So I say, how dare you criticize me when you are not a practitioner? Right. You need to put time first, not into impressing other people, but actually doing the work before you have legitimacy. If you don't make cakes, you can't argue with a chef about how to make a cake. That's not appropriate. You are pretending to be something that you're not.
Right, a shoemaker should not bake cakes.
Well, that's another thing. But the point is, you know, you should have some sense of modesty that you cannot criticize a practitioner. I mean, you know, it's just inappropriate because you are not familiar with the skills of doing it. And moreover, if the practitioner is following the scientific method by collecting evidence. Now, the argument is, oh, Avi Loeb gets a lot of attention. He wrote these diary reports. Why did he write it? He should have waited until a scientific paper was submitted for publication. And I say, no, I'm using it as a way to let the public know how science is done. I'm showing, you know, that we go to the Pacific Ocean. We don't necessarily find what we are looking for. Then we do find it. We make mistakes. We do. So then the public connects to that because it sounds human. It sounds completely natural. That's the way anyone, I don't feel superior relative to non-scientists. I'm just describing what I'm doing and they resonate with that. Why is that a negative? Why do I have to wait until I have the formal, technical, scientific paper and only then deliver the final answer in a conference room of a press release? That to me sounds completely unnatural because you are pretending to be more than you actually are. I was describing what happens on the ship. And these colleagues find it offensive for me to communicate with the public. Why? I also have the scientific paper. I actually I woke up at 3 a.m. this morning because I'm editing the scientific paper. I work really hard about it. From 3 a.m. until the two of us met, I was working on the scientific paper to be submitted, hopefully, by the end of August. And I'm working around the clock on this paper. When I was on the ship, I worked around the clock. I slept maybe a few hours and then had to wake up in order to go to the run of the sled. We had a magnetic sled collecting magnetic particles from the ocean floor. So it would sometimes return the materials in the middle of the night at 3 a.m., 2 a.m., midnight. Whenever it came back to the deck of the ship, I had to go there and scoop the materials together with team members.
Right.
So the point is, I'm putting the effort, doing the heavy lifting, and for other people to say that it makes them sick makes zero sense, because I'm going after material evidence. So you can argue about the interpretation of what we find, but for that you have to wait until the material. So people expressed opinions before we give the results yet, and that's another. So what I'm trying to describe is, first of all, academia, and second of all, the practice of science are not what they are supposed to be. And the reason the public doesn't know about it is because the communication with the public always takes place as the final product comes out.
Right.
And then a press conference of the results from a paper that was refereed. And sometimes those results announced at the press conference turn out to be wrong. And then it's very embarrassing. Right. And then people say, don't ever speak about the mistakes we make along the way before we arrive to the press conference, because the public will get a negative impression. And I say it's actually the negative impression is in the delivery process of just showing off to the public the final answers.
Because that shows that you're an elite.
Yeah, exactly.
Above the public.
Exactly. Right. And by the way, I was born on a farm. I don't feel as part of the elite. I truly connect better to people who come to fix, plumbing problems that I have at home, the sewer, whatever. I can speak for hours with such people, and I enjoy it more than speaking to my colleagues in academia. Because when you have authentic people that are not trying to show off, that do not try to use whatever circumstances there is to demonstrate that they're smarter, it's much more enjoyable. And, like the team on the ship was like that. They were not from academia. Each of them were trying to make the best contribution so the mission will be successful. And they did it selflessly, and they did it in the best possible way. It's just like playing sports, and I love sports. I jog every morning at sunrise, and we played soccer just a few weeks ago against the students. So the point is, when you play sports in a team, you feel a connection to the other team members, because it's not about showing off. It's about winning the game, and in order to do that, you need to work with your team members, and
keep your eye on the ball.
Keep your eye on the ball, and also you are being judged by the outcome. Right. It's not, if you are a string theorist talking about extra dimensions and you never get tested in your lifetime, right. That's like not even, kicking the ball. In the context of physics, you need to make a connection with reality to test your ideas. Right. So if you want to score a goal, you need to kick the ball, and it might miss or it might go in, depending on what the experimental data shows you. But if you have no experiments, it's like you don't do anything. It's like completely virtual. You can put goggles on your head and live in the metaverse. That's the idea of the metaverse. But to me, it's just like, recreational drugs. You feel good about yourself, but it's not the reality that we share. And I'm really interested in understanding the reality. If we have a cosmic neighbor, that would be extremely exciting.
Right. So with that, I'd like to talk a little bit about your upcoming book, Interstellar. The greatest weird thing, which is that the military is ahead of UAPs than scientists. Right. So why is that strange? Well, it's because the scientists should be on the forefront of cutting edge physics.
But there is a simple explanation to that, which is that astronomers, they look at the sky, but they train their telescopes to look at a small region of the sky most of the time, and also to look at very distant sources at the edge of the universe. Whereas, if a bird flies overhead, they ignore it. However, for the kind of reports about anomalous objects that the military personnel talk about, you have to look at the entire sky. And the US government is doing that for national security reasons. They want to know if there is any ballistic missile headed towards the US, or a spying balloon or whatever. So they have to watch the sky, and they would be the first organization to notice it.
Right. But as you say, the military is not well equipped to do that, right? Because, as you said, they don't analyze the whole sky.
Yeah.
But you know, the military's release of the report on UAPs was the initiative for founding the Galileo project, right?
Right. So that happened. Well, it was the Director of National Intelligence that delivered the report to the U.S. Congress in June 2021, and then there was a second report a year later, 2022, and then there was a new office established in government called the All Domain Anomaly Resolution under the Pentagon, and the purpose is to look at all reports from military personnel, like pilots, who see unusual things and try to figure out what these are, okay? And the director of that office reported recently that only a few percent of all the anomalous objects are actually anomalous, that the rest, they can figure them out, like balloons, drones. But there is still a few percent, which means that we're talking about of other tens of events that they cannot figure out every year. And the fundamental question is, does any of them show evidence for an extraterrestrial gadget that we did not produce, our technologies cannot explain? And there was a hearing about that in Congress, and two of the pilots were talking about it just this year, a month ago, and then there was a testimony under oath by David Grush, who said that the U.S. government has in its possession materials and alien spacecraft that, and there are programs of retrieval and reverse engineering of those spacecraft, and that he spoke with 40 people that have direct involvement in those programs, and that he himself never saw it, but he has the contact information for those people. So the Congress people asked him for the details, the contact details, and presumably they will go after this evidence and try to find those people. And we shall see what comes out in the coming months, because if this story is fabricated, which is a possibility, people can say anything, then we will not hear anything. But if the government does have in its possession some materials, I would like to see it. I would to help the government. Government is not a scientific organization, so first of all, they have no reason to hold it close to their chest.
Because it's not a national security threat.
It's not a national security because
it's an extraterrestrial.
Yeah, and it came from far away, thousands of light years away, and probably took more than millions of years to travel the distance. So humans were not around. Humans just came to exist as a species on Earth a few million years ago. So we were not around, and obviously, when it started its journey, it doesn't care about humans. But also, even if it arrives here, why would it care about how we split the land on this rock that we live on? So it has nothing to do with national security. This should be scientific data that is shared by all humans, because we all deserve to know. And it's just like the idea that you go out from an isolated family, you go out to the backyard, you find a tennis ball from a neighbor, and then you can decide to tell your family members or not. And I think it's completely inappropriate to hold it off, because your family members, knowing that they have a neighbor, might decide to close off the curtains so that to maintain privacy. And they might decide to go out and chat with the neighbor or learn from the neighbor. But at any event, even if you do nothing, the neighbor might come over and knock on your door, or the neighbor might affect your life, your family's life. So to me, it sounds,
or you can learn from the neighbor.
Or you can learn. So to me, it sounds completely inappropriate to hide any such information. It's better to be aware of the neighborhood that you live in so that you can adapt to it.
Right. And so, and then you talk about how the Galileo project is working to detect these UAPs. Right. So you decided to put the first observatory on top of the Harvard College Observatory, exactly. Right? So why did you choose that as the first prototype for the project, given the fact that, as you say, it has a lot of pollution and...
So we started there because it's close to my office, close to the offices. But as of now, we put it in a more remote site within Harvard University property. Okay. And the observatory is already operating right now. And basically monitoring the entire sky in the infrared, optical, radio, and audio. And the data that comes in is analyzed with machine learning software.
So it's trying to identify what is ET or what is non-ET.
Right. So machine learning means that you are training it on objects that are familiar. So when you have a large enough data set, and it could be training on things in the internet, but it also could be on in real life. Eventually, the idea is that it will recognize natural objects like birds or human-made objects like balloons, drones, airplanes. And the question is whether there is anything else extraterrestrial. And the difference from the government's approach is that the government is interested in national security. So they want to know if it's made in China, made in Russia. For me, it's the most boring kind of information. I'm interested in whether it's made on some distant planet. And even if it's one object out of 1,000, that would be a very important news as far as I'm concerned. But the government wants to know what all of the other objects are. And so we are complementary in our interests with the government. But moreover, the reports that came from military personnel, they were anecdotal. Some pilot happened to be at the right place at the right time. And you cannot tell from anecdotal reports how anomalous something is, because to do that, you need to watch the sky all the time, and that would allow you to calibrate the noise. You know, if you see balloons, you see drones very often, you know how frequently they are. And then if you see something anomalous, it would be really anomalous relative to that noise. And so in science, in physics, it's all about the signal to noise ratio. For example, some people advocate going to war zones like Ukraine. And I say that's the worst environment because there are so many things flying in the sky. Well, artillery shells, bullets, and drones, and actually satellites, espionage. It would be the last place I want to put my sensors next to.
You talk about Ukraine in the book, how Ukrainian scientists reach out to you about a lot of alien sightings, but those actually turned out to be ballistic missiles or artillery shells.
So science is about signal to noise ratio and not so much just about signal, because your signal may be, noise. And to figure it out, you need to go to regions where the noise is very low and see if you see a signal. And so we will make copies of the first observatory that is already working. The first one will go to Colorado. We are already putting it together. And then make more copies depending on funding. We need funding to do that and place them in many locations, hopefully tens of them, maybe 100. And so that will be the scientific approach to figuring out what unidentified anomalous phenomena are. Once again, it's about evidence. It's not about people talking about it, because for decades people were talking about it.
Right. Now, let's say, hypothetical thought experiment. If you see an anomalous object on the Galileo project, what would your first course of action be? What would you do?
So first thing is to check whether it could be anything familiar. And for that, you need exquisite data. You need better data than usual, just to make sure. And then suppose we realize, oh yeah, this is technological for sure. It cannot be a bird. We measure the distance. It looks like a big object and it looks like technological. And yet it maneuvers in ways that our technologies cannot reproduce. That is, it's doing some strange maneuvers. Then we write it up as a scientific paper, and we let everyone know about it. Now, nobody came to me and said, "Oh no!" At that point, just don't disseminate this information. Nobody from government or anywhere. So the thing about bringing this to the realm of science is that science is about open knowledge, and everyone should know it. So that will be the approach. Then, what to do after that? Day 2, after you discover that, that really depends on what we find, and I'm against the idea of having a committee decide about a protocol, like saying, if you see this, you do that, if you see this, because the committee has very limited imagination. And it's better to just wait and see what we find and figure out what this thing is seeking. Because if you have a visitor to your backyard, better, the first thing to do is figure out the nature of the visitor. What's the purpose of the visit before you decide how to respond to that.
Right, right. And you say in the book that to make a follow-up observation on a spacecraft or some UAP, you would need a $1 billion kind of rocket to reach that.
That's only if we want to chase an object like Oumuamua. It's billions of dollars. But on the other hand, going to the Pacific Ocean, for example, if there is a meteor that collided with Earth and it was just like the Voyager spacecraft, made of materials much stronger than iron and meteorites and moving very fast, like this meteor from 2014, that costs 1,000 times less. The expedition was $1.5 million. So it's much easier to find things that crash on Earth because you can then retrieve the materials to have a rendezvous with an interstellar object along its path is much more challenging for several reasons. One, these objects are moving quite fast, faster than objects that are bound to the sun. So you need to anticipate their orbit at the right place at the right time and then launch something that will sort of catch up with it. And then to land on it is really difficult because you need to follow it at almost exactly the same speed, get closer, and then eventually land. Because if you just collide with it like a bullet, you would create a crater, nothing would survive, no instrumentation would survive, you wouldn't be able to figure anything out. I mean, you might transmit some images as you are crashing.
Like dark.
Yeah, maybe that can be done, like a camera, a cell phone, sent and just for the purpose of crashing.
Or eject a mini probe that crashes in and then capture some fragments that.
Yeah, so that can be in principle done, and but it's very expensive, and it would be fascinating to see an image from up close because you can tell the difference between a rock and a gadget easily.
First of all, you chair the Breakthrough Starshot Committee.
Right.
So can you explain a little bit about what Breakthrough Starshot is, how it hopes to get us to the closest exoplanet?
May 2015, an entrepreneur from Silicon Valley named, he's also a physicist, has a background in physics, Yuri Milner, came to the Center for Astrophysics where my office is, entered my office and sat on the couch and said, Avi, would you be interested in heading an advisory committee about a mission to visit the nearest star system within a couple of decades during his lifetime, my lifetime, we are the same age. And I said, sure, but I need 6 months to figure it out because it's not clear that there is a method. I know the distance to the nearest star is 4 light years, so it takes light 4 years. And you need to get there in 20 years, you need a spacecraft that moves at a fifth of the speed of light, which is 1,000 times faster than the fastest rockets that we launched. So it's just like the transition between Henry Ford's first car and Sputnik. That's the difference in speed, a factor of 1,000. So we made this transition in 50 years, with Sputnik, but now it's time to make another transition by a factor of 1,000. And so for 6 months, together with my students and postdocs, we were brainstorming about what method can do it. And then I wrote one paper with a postdoc of mine on the possibility of using a light sail, basically just like you use a sail on a boat to propel a sailboat by it reflecting wind and as a result being pushed. And you can push a sail, a very thin membrane, with a very powerful laser. And that could help reach speeds close to the speed of light because you are using light. So you can do that up to the speed of light.
So you are basically leveraging radiation pressure to speed something up.
Exactly.
But wouldn't the laser get less powerful as you get far away?
It does. But so you need it to be sufficiently powerful and focused. And eventually, after many conversations for many hours with Yuri Milner discussing it, he embraced this idea. And I should say that just before presenting it to him, I was visiting Israel at the time, and we were about to go for the weekend, for a vacation on a goat farm. And I got a phone call from the assistant of Yuri Milner saying that he wants me to present my conclusions within a week after I get back. And so I said, okay, well, we went to that goat farm, and I had to prepare my presentation. And there was no internet except at the office of that goat farm. So at 6 a.m. in the morning, the following morning, I was sitting with my back to the wall of the office of the goat farm, looking at the newly born goats that were born just a day before, and typing in the PowerPoint presentation about the first interstellar trip that humanity can make. And I'm sure the owner of this goat farm never imagined that in that goat farm there would be a PowerPoint being, prepared about that idea. So I presented it to Yuri, and he liked it, and then we discussed it many hours, and ended up with a concept that we can use a very powerful laser, 100 gigawatt, that will shine for a few minutes on a sail the size of a person that is outside the atmosphere, because otherwise in the atmosphere there is friction with the air. You don't want that. You want to put the sail outside, and the laser will go through the atmosphere out to space and push the sail. And if the sail weighs just a few grams, then for a few minutes, 100 gigawatt laser can bring it to a fifth of the speed of light, across a distance that is 5 times the distance to the moon. And then it's just like a bullet. It goes straight to the target. So you just need to orient it properly. It takes 20 years to reach the target, the destination. It takes a few minutes to accelerate it. So this is an unusual journey. Within a few minutes, you reach a fifth of the speed of light, and then you just coast for 20 years. That's amazing.
So it only has a camera, right? Nothing else?
Well, yes, a camera, maybe magnetometer. But the point is, it's a first demonstration that we can leave the solar system on a short time scale. I mean, if we were to use chemical rockets, it would have taken us 50,000 years to get to Proxima Centauri, the nearest star. And that means that we should have sent the rocket back when humans left Africa, the first humans left Africa 50,000 years ago, for it to arrive right now. So it's a very long journey. And, obviously we will not have patience, because in 50,000 years, who knows what technologies will be available. So the point is, there are 3 challenges here. One is to make the laser beam, that's the engine.
Right, to collimate the laser so it doesn't spread out.
Yeah, and have enough power. The second is the sail materials to be, strong enough in a thin film that will maintain the radiation pressure and not buckle or do anything. And then the third, the most significant challenge is communication. But we realize that there are no showstoppers, and we are now working on these 3 technologies. That is the main focus. In fact, a month ago, I chaired the meeting of the project. We have various teams working on the different components, and it doesn't look like there are showstoppers, but it will take a long while to develop this innovative technology, like any innovation. But to me, another interesting point is, if we are thinking about it, someone else might have developed it. And another civilization sending a tiny craft, that is just a gram in mass and size of a person, such a thing would not be noticed, because our telescopes are not sensitive enough to see the reflection of sunlight.
Right, from such a small
it's
object.
100 times smaller in size.
And too fast to be.
100 times smaller in size than Oumuamua was. So it's 10,000 times fainter, because the reflection of sunlight is according to the area of the object. And as you say, if it's moving so fast, then astronomers will just see one data point and then it disappears, and they would think it's a statistical fluke, it's not a real object. They will not see the trajectory. Nobody would pay attention. It may exist, we don't know. I mean, there might be, actually this meteor that we went after in the Pacific Ocean is about a meter in size, was a meter in size. And we calculated, based on the fact that one such object was detected over a decade, we calculated that there should be 10 million of those within the orbit of the Earth right now, within the orbit of the Earth around the Sun, because the Earth has a very small cross-sectional area to collide with one of them. So there are many of them, but we can't see them because if they don't collide with Earth, they just reflect too little sunlight. They are too faint, you can't see them. When they collide with Earth, they generate a fireball because of the friction with air. So they release a lot of heat. That's the reason that, for example, this meteor was discovered, that it was not a reflection of sunlight, it was the flash of light generated by the explosion of the object. Just like an atomic explosion. It released a few percent of the Hiroshima atomic bomb energy. And if you watch Oppenheimer, this movie that came out, you can see the immense fireball that is created. They looked at it from a distance in Los Alamos, where Enrico Fermi was. And by the way, the reason he was because of the development of the nuclear bomb. And he was part of the Manhattan Project. He was probably the key physicist to the success of the mission because he was an exceptional experimentalist, but also knew the theory extremely well. You know, I read many of his writings when I was your age because he had a very good intuition, understood the physics in a deep way. So he combined experiments and theory in the best possible way. And they looked they looked at the fireball in Los Alamos, and it's just like a mushroom but when an object comes from the sky, it explodes in the higher atmosphere, so it doesn't cause much damage. Actually, every year there is a collision of Earth with a rock the size of a person that belongs to the solar system. Every year there is an atomic explosion, roughly energy output of the Hiroshima atomic bomb. We don't hear about it because it happens at an elevation of 30 to 40 kilometers above the sea level, so it doesn't cause much damage. We hear every now and then, once a decade, once every few decades, about a meteor that happens to damage some homes, or if it collides with the ocean, it may generate a tsunami if it's big enough. But most of the time we don't hear about it. But every year you have an atomic explosion in our atmosphere. And the other thing to keep in mind, on Mars, there is very little atmosphere left. That's why Mars lost its oceans. So I calculated that suppose you had a city like New York City, okay? On Mars, when life was possible, like 3 billion years ago, when Mars had an atmosphere, had liquid water, suppose that intelligent life developed twice as fast on Mars than on Earth. That's possible, just a factor of 2, They had similar conditions, life started earlier on Mars. And so it's possible, suppose by a factor of 2, that Mars was ahead of the Earth in terms of developing intelligence. If there was a city like New York, and then Mars lost its atmosphere and became a desert, the way we see it now, I calculated that over a few billion years, there are impacts of rocks, because for Earth, the rocks are stopped by the atmosphere. And that is like a cushion that protects us from small rocks. But on Mars, there is no significant atmosphere. So all the rocks bombard the surface, the big rocks, like a meter in size. And I calculated that there were more than 20 atomic explosions equivalent for every square kilometer on Mars. So if you had a building for every square kilometer, everything would be devastated. Like New York City.
So 20 Hiroshimas for every square mile.
More, if it's mile, then you have another factor. So it may be 40 of them for every square mile. So just think about New York City, every square mile, you have 40 Hiroshima explosions. What would be left of the city?
Right, the crust. But back then, Mars would still have an atmosphere, right? Or at least a little atmosphere.
No, that's when that's when life may have existed. But I'm saying since then, so today we will not find any high rises. There would not be any high rises even if they existed 3 billion years ago, because they would be demolished by impacts of asteroids. And this is a simple calculation that one can do. It's just amazing that the entire surface is being ground down by impacts, very energetic impacts. Now, my hope is if I ever have the ability to design a mission that will go to Mars, it would be to send drones with cameras into the caves on Mars. There are these lava tubes, just like in Hawaii, where the flow of lava from volcanic activity, developed a crust at the top, and then under the crust, the flow would continue. So you end up with a cave. And you see that those caves, they're beautiful in Hawaii, for example, where there was a lot of volcanic activity. So on the moon and on Mars, you can also find those lava tubes. And those are the best places to go to be protected from the surface environment, because on the surface right now the temperature changes by hundreds of degrees between day and night, and also there is bombardment by very energetic cosmic rays. So when Elon Musk said, I wish to die on Mars, I don't wish him that, because going on the surface of Mars would be extremely risky right now. You want to go into caves because they moderate the temperature variation, they protect you with a crust, the ceiling, they protect you from energetic cosmic rays. That's the place to go. But if I ever go there, or if I send drones to examine them before we go there, I would like to see if there are any wall paintings by prehistoric intelligent beings that, or any skeletons inside these caves. Nobody checked, and it would be interesting to.
You know, the Ingenuity helicopter on Mars right now should go search for LGMs in the little caves.
Yeah. One thing about engineering, I should tell, this is a helicopter, and it's part of the mission with Perseverance, which is a robot. And these are being operated by engineers in the Jet Propulsion Lab of NASA. And I call that helicopter parenting. Literally speaking, you are parenting a helicopter, but you're also helicopter parenting these devices. You're telling them what to do. And just like parents, can be very helicopter-like if they tell the kids what to do. And this is not, these are the most advanced devices that we send to Mars, but it's really not very impressive, because you can't do that when you go interstellar, because it takes so much time, even for your signals, the light signals, to reach your probe. The probe cannot wait for your guidance. The probe has to think autonomously.
Right, and, AI.
Yeah, so that's why I'm thinking about artificial intelligence, AI astronauts. And they would be thinking for themselves and deciding what to do. They don't need guidance from the engineers in Pasadena. They will just, and by the way, nature does it all the time, because you look at dandelion flower, it has seeds on it. And when they get carried by the wind, there is no umbilical cord connecting the dandelion's flower to the seeds. The flower doesn't know what the seeds are doing, right? It's not like telling the seeds, go there and fertilize this piece of land. The seeds just go, and the hope is that, with the wind, they will be carried far enough and they will make more dandelions. So they carry the DNA, and that's it. You don't need to communicate with the sender. And the same can be done in interstellar space. You just send those gadgets that think for themselves, and then they figure out what to do, but they carry your mission. You tell them in advance, you give them a blueprint of the mission, and then the idea is that they will carry it forward.
Right. Professor Loeb, I'd like to talk a little bit about your work on black holes. You're the founding director of the Black Hole Initiative at Harvard. And in fact, Stephen Hawking came to your home to celebrate that initiative. So I'm honored to be in a place that was near where Stephen was.
In fact, he came through this porch, through the door, because we had to build for him a path that he could go on with his wheelchair.
Good evening, and thank you to Avi Loeb for hosting this evening's Passover celebrations. Thanks to Avi, Andy, and Yuri Milmer, I am here again and hope to return soon in support of the new Black Hole Institute.
We will be delighted to host you every year, and assuming that you will not solve the information paradox very quickly this year, there will be a lot of opportunities for you to work with Andy and Malcolm in future years, and we will be delighted to have you every year. And it was funny because a few years ago, my daughter, she now finished college, but she was dating a kid, and the kid said, "Oh, you live in this house. My grandfather built the rail for Stephen Hawking, who visited this house because there used to be a famous physicist that used to live in your house." And she said, "That's my father."
Okay, yeah. So, you know, a lot of your work on black holes is fascinating. I'll just probably look at some of the highlights. One of the most amazing things you did is one of your predictions that got confirmed is that there are hotspots around Sagittarius A star, right? Can you explain that for a little bit?
Right. So about 20 years ago, I had the idea that suppose you have a flashlight that is moving around a black hole, and you watch the flashlight moving, you can actually map the space-time around the black hole, because the way the flashlight moves will inform you about how space and time are curved in the vicinity of the black hole. And back then, I went to a few colleagues that were much younger than I am, and I said, look, this can be realized in nature. If you have a hotspot, a spot of hot gas that is somehow confined, and then it moves around the black hole, you can watch it moving around and learn about the space-time. And they said, no, that will never work.
There will be no stable orbit around the black hole.
Well, not so much. There are stable orbits outside of a certain distance from the black hole, and that distance depends on the spin. But the issue is really that in any configuration where you have gas, the part of the cloud of gas that is closer to the black hole will move faster than the part that is farther, and it will be sheared out. So basically, you'll destroy whatever. And they said it will not survive even for a part of the orbit. And also, having such a thing that is hotter on a spot, may not exist in nature. I was actually motivated by the sun, because you see hotspots on the sun. And I said, well, maybe, because we know that there is magnetic turbulence around the black hole. So I said, maybe the same situation happens there, and there would be a hotspot that maintains its integrity. Anyway, they said, no, it's a waste of time, not worth it. And like many times back then, I believed them. I wasn't mature enough the way I am now to say the hell with what other people do. It came with age, because at some point I said, forget about it. I don't care what other people say. I'll just do what is right. So back then, they said, no, it's not worth it. And then I came back to Harvard from the sabbatical that I had at Princeton when I had the idea. And I mentioned it. A new postdoc came to work with me. His name is Avery Broderick. And he said, I just finished my PhD at Caltech, and I have a code that can solve for the propagation of light rays near a black hole.
Okay.
And that was my PhD, and I just want to use it for something. And I said, great. Why don't you use it to calculate what we will see from a hotspot moving around a black hole? And we did it with him and wrote 5 papers on this. And then a Scientific American article about it. And people said, oh, yeah, but maybe it's not there. And then, so that was all around 2000. And I came back from the sabbatical 2004, and then 2005. And then in 2017, a team in Germany developed a high-resolution imager that can look for the center of light near the black hole at the center of the galaxy. So just looks for the pinpoints, even though it can't image the vicinity of the black hole because it's so compact. What it can see in infrared wavelengths, it could see where the center of light very precisely. And what it noticed is that center of light is actually executing a circular orbit around the black hole. which is like a hotspot. And they referenced the paper 12 years earlier and talked about the implications. And what is the moral of the story? That sometimes nature is more imaginative than we are. So when I thought about the idea, but my colleagues said, no, it's not worth it. Nevertheless, we ended up writing it. And I can imagine a situation where I wouldn't have this postdoc coming and we wouldn't write anything. But the point is, scientists are sometimes overly critical. I wouldn't say conservative, because like in the context of dark matter, there are all kinds of speculative ideas. In the context of string theory, a lot of speculation. So they are willing to do speculations, but for some mysterious reason, they have an objection. They say, no, this should not be done. Like the expedition should not be done. And very, very often that is the wrong approach. And there must be a lot of unborn babies. That's what I'm saying. That babies that, were aborted and never came to life simply because some scientist made a negative remark, and that scientist was highly regarded, and he said, no, this is not worth looking into. And you see a lot of situations where ideas are not being, fulfilled to their promise because of that. At the same time, you see situations where a very distinguished expert or scientist says this is worth exploring, and then a whole community works on it for 40 years, and nothing comes out of it.
It rhymes with string theory. Right. Thank you for your time.
Oh, it's my great pleasure. And by the way, the result that we derived in that work with Guillochon was that black holes can act as slingshots and eject stars close to the speed of light. So actually, there are stars moving near the speed of light, a fraction of the speed of light, throughout the universe. It's very difficult to find them, but they exist out there. And if you were to be on a planet near such a star, it's a very exhilarating journey, because you can cross cosmological distances. One thing I wanted to mention is, according to Einstein, if you were to board a rocket that takes you with some acceleration, you cannot tell the difference of that from a gravitational force, because you will be pushed against the back of the rocket as if there is gravity. So just imagine a rocket that is accelerating at 1g, the gravitational acceleration on the surface of Earth. It would feel just like we feel right now here on Earth. And the thing is, within 1 year, if you accelerate at 1g, which is very comfortable,
you reach the speed of light.
You reach the speed of light.
Right, and in 20 years, you will reach the edge of the universe.
Exactly.
Right.
Exactly.
Yeah,
so
that was amazing.
The only problem is it's not easy to build such an engine.
Yes.
I actually have an idea of how it's possible, but I'm working on it right now. Hermann Bondi was a physicist in England, and back in the 1950s, he wrote a paper saying, suppose there was a negative mass, okay? So suppose you have Earth, and then you put an object that has exactly the same mass of Earth, but negative mass. What does it mean? Negative mass, think about it just like electric charge. So a positive mass attracts according to gravity,
Okay.
and a negative mass would repel, okay? So that's the idea.
Okay.
So what would happen if you put next to Earth an object with the same mass that is negative? So that object would push the Earth away, and the Earth would attract this object together with it.
Okay.
So you'll end up with the two of them, the pair, moving together and getting accelerated, because the negative mass would keep accelerating the positive mass, and the positive mass will keep pulling the negative mass with it. So this system of positive and negative mass, which is called the dipole in the case of electromagnetism, this system will reach the speed of light because it will keep accelerating forever. So that's one engine, and it doesn't cost you anything. You just need to find a way of engineering
a negative mass.
Sounds
simple. Okay.
It's not so easy, but that's what I'm working on right now.
Okay. Well, thank you for your time again, Professor Loeb, and with that, make sure to like, share, and subscribe, folks. Okay.
It was a pleasure.